any of these problems. I can give you some equations with 15 different reactants and products, but if you know the process, you're good. You know how to go for it. So whenever it's something stated like this for a reaction, it says synthesis. Synthesis means takes two reactants down to one product. You got that so far? What are the two reactants? Al2O3, so aluminum oxide, and H2O. And what does a metal oxide and water come together to make? A metal hydroxide. In this case, was aluminum hydroxide. Okay, so we got that balanced out. Second, the question gave us information about grams of aluminum oxide. So you started with the given. The question was to get to moles of moles of the product. The product is not a secret anymore. We know the product is aluminum hydroxide. So really what's the question is, what are the moles of aluminum hydroxide? So if you start off with grams of aluminum oxide, what's the next step? So go to moles of aluminum oxide, and then you don't care about aluminum oxide anymore. You want to go to, so how do you get to aluminum hydroxide? A mole ratio, and that's where we stop because it says go to moles. That's it. So where do you find your mole ratio? That's where you find your BCE. 2 aluminum hydroxides to 1 aluminum oxide. You would have gotten a 1.92 moles. Oh, who got that? Yes. Okay. Questions before we move on? If you did not get this, you need to be writing down ferociously. I'm not waiting on you. Okay. Oops. So the next question said how many moles of water, so question moles of water, are needed to react with 3.367 moles of aluminum hydroxide. How many steps would this take? One. Because what is the one step we need? Just look at the mole ratio. You're like, I got moles of one thing, moles of A, I'm going to moles of B. It's one step. And that's where the BCE comes in, and you find the ratio between water and aluminum oxide, and that's a 3-to-1 ratio. And that would give you 1.1 moles of water, 366. Who got that? Yeah. Oh, I'll come for it. Okay, the next one, how many grams of product? So again, the secret is it's no longer a secret. We know the product is aluminum hydroxide. Are formed when you have 67.2 grams of aluminum oxide. So if you're starting with your grams of aluminum oxide, what's your next step? Convert to moles, and then you're in moles of aluminum oxide. That's why it's important to write the identity. If you just put moles, I would take off credit because I don't know moles of what. Now it's really important to know what you're talking about. So moles of aluminum oxide to mole ratio to moles of aluminum hydroxide, and then to grams of aluminum oxide. If you don't know your flow map, I gave that to you as a helpful guide. It's not going to be a crutch. You don't get to use it. It's a simple process that you need to know. So when you get that finalized, oh, by the way, where am I getting these numbers? Here on the table, right? Just add it up. So once you get there, you should get, what did you guys get for your grams, those of you who did it? 103 when I rounded. Well, it really does depend on what numbers specifically you got, so it does vary. But around 101, 105, that's cool. That's 3 sig figs is the way to go. Okay, so who's got 10 for 10 so far? All right, that one's not bad. That one was easy. The next one required you to first write the BCE. Who wrote the BCE down? It literally told you 2 reactants. If you see ionic and ionic, you should know it's double replacement. And then from there, you had to read a little further. We did this first part in class. I'll stop right there for a second. So we talked briefly about molarity yesterday. The units of molarity are whatever what? Of liters of solution, right? So in your head, you should be thinking of liters in two different worlds. Liters in gases, what number comes to mind when you think of liters of gases? 22.4. And then you think liters of solutions, that's molarity. That's a whole totally different liter kind of theme. So the liters in this case are usually given actually as milliliters because they're small volumes, and then we convert somehow. So remember, M times V gives you moles, but what does V have to be in? What unit? Liters, because if big M is moles per liter, you have to have it in liters in order to cancel out liters to simply get moles. So we all are comfortable when we get the moles to pretty much go anywhere else, except for part B probably, and we're going to get there. So whenever you're given this, what's the very first step you have to do with this volume?
Times 1,000.
So divide by, divide by 1,000. So you move the decimal back 3 places. So then, that's me right there. So there's my liters. timesing by the molarity. I'm going to go ahead and flash this whole thing. I can go slow enough here. So whenever you're given two pieces of information about one reactant, you must use them together. That's why I multiply them immediately. I went ahead and stopped and said this was my moles, and we all got this far yesterday. But this is not just moles. This is moles of sodium sulfate. This is specifically sodium sulfate. The question was how many grams of precipitate will form. Well, if you don't know what the precipitate is, you probably had to go back and use your solubility rules and realize that sulfates are all soluble except barium, strontium, calcium. So barium sulfate is our precipitate. So I use my moles of sodium sulfate and use my what here? Mole ratio to get from sodium sulfate to barium sulfate, 1:1, and then I use the molar mass of barium sulfate to go to grams. So that was not a simple process, but once you got to moles, you should have known what to do from there. Specifically, you'd written your BC first. So that was 0.28 grams. Who got that? Okay, a couple of us. All right, so the next one has a little bit of a spin on it. So the question gives you similar information about volume and molarity. So what automatically do you think you should do with that? Those both are knowns together. What do you do with those two knowns when they are given to you? Somebody just told me. You multiply them, right? But that would have to be in liters first before you multiply. So you know when you multiply M times V, what unit do you have now? Moles of sodium sulfate, right? So our question says how many milliliters of this barium nitrate solution do we need? Well, I already can see I'm going from sodium sulfate to barium nitrate. So what process is that? From A to B. Moles of this one to moles of that one. Okay, I can easily get to moles of barium nitrate. But then you're like, how do I get to milliliters? Well, if I give you the molarity, what are the units for molarity again? Moles over liters, right? That's a conversion factor. Do you have to use conversion factors in one way, or can you flip them? You can flip them. So what happens if you flip that? What's on bottom now? Moles. And moles could cancel if you used it, right? What would be on top? Liters. And could you take liters to milliliters? Yes. So use molarity if needed as a conversion factor. In this case, we did. So
don't we use molarity? Does it have, if we're going to call it molarity, does it have to go to milliliters after liters?
No, sometimes I'll ask for liters. Sometimes I'll just ask for volume. So in this case, I didn't actually stop at all through this whole process. I went straight from liters in molarity to get to moles of sodium sulfate, because you can see my liters and liters cancel. So that's moles of sodium sulfate. That I went 1:1 ratio from the BCE to get barium nitrate. And then I took barium nitrate's molarity and I just flipped it to put the moles number on bottom and the 1 liter on top. And I just cancel the whole way. You can stop in the middle, take a breath, and then continue, but it's just up to you on how you got to do it. From there, you should get 500 milliliters of barium nitrate. 500? Who got that? Yeah? I saw someone who got 50. Double check your math and my math.
This is where, like, okay, this is what I was thinking. I'm not sure. I just thought it was right. So, like, the first part was 0.01, so you're doing the 0.05 times 0.01. And then that middle part is just 1 times 1.
Because that's what I was thinking, looking at it. I think it should be 50.
And then you're dividing by 0.01 again.
So basically, those cancel. That's why I think it should be 50, but I don't know why I put 500.
That's what I was thinking.
Did you check your math? I haven't checked my
No,
math.
I mean,
So it might be 50. It probably is 50, mathematically. I don't know why that whole thing's there. That's a decimal. So after, in hindsight, looking back at it. But you can see the process of using molarity as a conversion factor. That was the main point on that one. Okay, so then on the last one, who even got down to the last one? Okay, this one didn't require much knowledge past maybe what we did yesterday. What did you start with? Barium sulfate, right? And you're going to grams of the other product. What's the other product? Sodium nitrate. So if you're going from moles of barium sulfate, what immediately do you go to? Moles of barium sulfate to moles of sodium nitrate, which is just other products, so that's mole ratio. And then how do you get to grams? Multiply by molar mass. That didn't require anything new. So those of you who said I gave up, you didn't even go down to part C. That's something that you easily could have gotten mole ratio from, and then grams. That's stuff we did at the very beginning yesterday. 425 grams? Okay, so I actually took 8 problems that were A through D, and I dropped it down to 4. We did 2 in class, and I asked for you to do 2.5 at home. So I already do make effort to limit what you guys have to do on your own. I'm trying, but I need some reciprocation of that. Okay, so before we start new stuff, I have a demo for you. Okay? We'll come back to this in just a second. I'll leave that there in case you did not finish writing. So people in the front, you might need to move. I have a pumpkin for you. Yes.
Real quick, is our foldable due today or tomorrow?
No. Foldables due on test day. Next week. We took me a small beaker of water. Like a 50 or 100.
Is that just about it, or the pumpkin part?
I'm not gonna say anything.
What?
Because I'll move. It's gonna like come out of the eyes or something like that.
It's gonna be awful. It's gonna be everywhere. I cleaned it up between 3rd and 4th period. Get a small beaker. Find one. Small beaker, halfway filled with water. Or I'll come get it. They're everywhere. Okay. So, how would you like to guys this have 4C, 425. Huh?
No, I was kidding.
Well, no promises on the first round, but you can try. I'm gonna try. Yeah. Okay, if you're good sitting there, Madison, I'm just saying. Just trying to protect that face. Alright, so this is calcium carbide. Calcium carbide is somewhat, it's pretty inert by itself. It's going to create, when put in water, a flammable gas called acetylene. So, put my little Mr. Jack-o'-lantern. His name's Jack. I know, very creative. He's just sizzling on the inside. Smells bad on my hand. Oh, extremely corrosive to eyes and skin. I should have washed my hands. But it will approximately make 150 liters of flammable acetylene if I put all this in there. I didn't put all this in, as you can see. Alright, so... Okay. It's flammable, right? So there we have us. Oh, that one eye just won't come out, guys. I don't know why. Okay, I'm gonna pop it out a little bit. Okay, give me the pieces back. Hurry. Where's the other one? We do not fail. We just try again. All the eyes have to come out. All 2 of them. Okay.
Maybe make the other arm loose.
Huh?
Maybe make that arm loose.
I did. Okay. I compromised it. Okay. So I'm just gonna let it kind of do its thing again. I don't know if there's enough gas in there. Maybe I should add one more piece.
The whole bottle.
I'm picking the largest pieces I can. Okay, so just give it a little time. It's brewing. It's nonsense here. I have another demo I'll do for you for pumpkins tomorrow. It's just 1 a day, people, until Halloween. We'll use this pumpkin a lot. Okay, I'm not sure on this one because I didn't put any more water, so no promises. Whoa! That was better! Oh my gosh, the water caught on fire! Oh my god. Amazing! Woo! Alright guys, no problem. Okay. Woo! Also, this is not bad. This is all I got. That's not bad. That was good.
That was funny.
Oh my god.
Go check out G6. That's really fun.
I don't care that I just...
Oh god.
Alright, so you wait now?
No.
Yeah.
Alright, so tell your friends, you know, chemistry fun. Oh, where's the eye? The mouth.
It's like my desk.
I need this took me forever. It took me 2 days to carve, okay? So 2 days. And I didn't work on it for 2 straight days. I just took my time. I made him have a sly smile. Okay, I'm not sure how this goes. It literally did. It took me 2 millions. I couldn't scrape the inside out. These little, like, these little pumpkin pie pumpkins, they're no joke. They are hard as a rock. So, there we go. Okay. Write down this right here. Let's go. I'm taking my glasses off. So I didn't actually do this. I wanted to do this with you yesterday, but I felt like you would prefer to have more practice in class. And some of us who worked through it, I think you feel better. After I went through that this morning, I hope that the rest of us feel a bit better. But on problem set 12, you'll have a bit of practice as well. So with percent yield, whenever we talk about percent yield, I didn't go over the notes at all, but what does percent generally mean? A percent of a whole, right? A part over a total times 100. That's what percent always means. So whenever we are calculating percent yield, we always base it off yield. Well, what do we yield in a reaction? Products, right? So these actual yield and theoretical yield, they're always products. So that's something to kind of consider as you're going through trying to read through a problem and figure out what to do with it. Also, what did it say actual yield was in your notes that you wrote down for warm-up? Okay, physically recovered actually in the lab, right? So this would actually be something that you would attain in the lab. But do you think I'm going to make you get up in the middle notes and go like, okay guys, go figure out the actual yield of this problem? Do you think I'm going to make you do that like right now? No. That would be awesome, but no, we can't do that right now. We can do it in the lab like a real lab, but not today. So this is probably going to be in the problem. This number that I give you, that's in the problem, is going to be called the actual yield. Theoretical yield, what did it say in notes for that?
The amount that can possibly be recovered.
Possibly be recovered in where? In what land?
Make-believe.
In make-believe land, in la-la land. It ain't gonna happen, okay? We are not perfect. We do not get the perfect yield that we think we're gonna get from a reaction. So when I put reactants in, I expect 100% of those reactants to react perfectly in unison, and I expect them to make perfect products, right? Perfect does not exist. So a lot of times our theoretical yield is a big number, but our actual yield is somewhat smaller, right? So this is usually in la-la land, okay? It's something you will calculate on paper, because paper is la-la land, and it's usually the bigger number. So actual yield is usually the smaller number. So generally, think about it. Think if you're a really good chemist, what would be a good percent yield? 50% is crap. 94, that means you're pretty awesome. Give me more. What's good yield? 96. 100% yield means you are perfect and you are not from this world. Okay? 99%. 85 is usually my cutoff. Like 85% yield's pretty good. So like 1% yield, 2% yield, 9% yield, bad, right? Yeah.
So you said that theoretical yield could be bigger or
Bigger
smaller.
than this number, right?
You said it sometimes could be smaller than actual yield?
No, I said usually theoretical yield is the bigger number. It's usually bigger than actual yield. I said actual yield was usually smaller than theoretical yield, unless I misspoke. But you know, I could just listen to the video and hear myself. But if you guys were like in the lab, you got, oh, I got 110% yield. What do you think happened?
Yes.
You did something wrong, right? Because that does not happen. Okay, so my jokes for you. We're on a boss at purifying. 99.6% yield. And this was us. This was AP Chem in one of our labs. I told them they could get more money for getting the best percent yield. We were all scraping crystals off the bottom of the beaker to get the best yield. So lab grade based on percent yield. Spent an hour pathetically scraping every last grain of product off the glassware table and floor, especially when your partner spills it and you really try not to strangle them. So Nathan Hayes, 2 years ago, Nathan Chem. Who knows Nathan? Nathan Hayes spilled the crystals everywhere. They crystallized on the table. They were beautiful, but they were on the table. So he was scraping them up. Anyway, okay, so let's do a problem with percent yield. And this will be it for yesterday's session. We'll start today's. So whenever you have a question, it says, what's percent yield? You're not actually looking for percent yield. You're looking for two pieces of information. Actual yield and theoretical yield. That's really what your question is asking. So you got to read between the lines. So I'm just going to read this at first. When 14 grams of magnesium chlorate decomposes, okay, so we got a reaction happening, and 3 liters of gas are collected, you're like, okay, well, what's the gas? We'll figure it out. At STP. Wow, a lot of information. Let's do baby steps. Let's start with givens. I want you to write down all the givens, and then we'll move on. Then you tell me what to do. So what are my givens here? 14.0, sorry. 14.0 of magnesium chlorate. What's that formula? 3, 2. Okay, what else do we know about that?
3.00 liters of
Okay.
gas.
I know this is decomposing though, right?
Yeah.
Okay, so I'm gonna just put an arrow there to remember we're gonna write a reaction. I know that I have here, right, 3 liters of gas. We'll figure out what that gas is in a second. And then what else? What conditions are present?
S2P.
Okay, what does that ring a bell? Or what does that mean to you?
22.4.
Right, I'm gonna write that down just for you to remember. 22.4 liters per mole is what that should be kind of whispering to you, those voices. Okay, so this information right here does not collectively make sense. Okay, so we need to kind of go further. What is the reaction here? What's the BC? I hear you, ClO3, 2, going to what? So, say again? So remember, chlorates make oxygen, not chlorine, right? So we know it makes oxygen, and then you kind of fill in the blanks. You're like, oh, it must be magnesium chloride. What is that? 2, right? Because it's crisscrossing charges, and balance. 3 in front of oxygen, and that's good, right? Okay, so now this makes more sense. What gas are we referring to? Oxygen gas. So I'm going to put 3 liters of O2. Okay, so we know this reaction's happening. We know we're making gas. What is the significance of this value? Label this in terms of maybe something given to us, the actual yield. This is the actual yield because 1, it's a product, and 2, it's a piece of information that's given to you that's referring to a % yield problem. And I told you I have to give you actual yield. So I'm not going to make Connor go like, okay, can you figure out the actual yields? We're waiting on you to finish this problem. So I'm going to give it to you. All right, so then what's the significance of this number? This is the what? That's not even a yield. That's a reactant, right? Okay, so what do you think I need to do with this number? And then
Figure out what the theoretical
yield
would be
of the oxygen. Okay, so note to yourself, anytime you have yields, they have to be in exactly the same units. Liters of oxygen is what we're going to. So what's our question? Theoretical yield of liters of oxygen. That's our question. So our question means get theoretical yield, and then we're going to plug it in to get % yield. So starting with the given, I was trying to get you guys to tell me this was the given, but that's what you're starting with. Lucas said to do what with it? Convert to moles. What's that molar mass? Get your calculators out. Latest, yeah. So you're just like thinking. Okay. So I'm doing like 1% yield problem today, 1 limiting reagent problem, and then you're practicing. So these 2 problems are like key. I'm asking you to have this for sample for homework. So what's magnesium's mass? I've heard you 24.31. What's chlorine's mass? Okay, but how many do we got? So 35.45 times 2 plus 6 times 16. What's your mass? 191.21 grams of magnesium chlorate. Okay, what's on top? 1 mole of magnesium chloride. I know it's so like tedious to write out the identity, but you'll thank yourself because you'll be able to understand what your work means. Okay, so I don't have any space, so I'm scooching down. What's my next step then, guys? Get just oxygen, but it's not from magnesium chlorate's oxygen. It's from the like legit oxygen made in the reaction. So what do I write here? The BC mole ratio, right? What goes on top? And you're pulling that from here, 3 moles of oxygen, and 1 mole of magnesium chlorate from the BCE of a 1 right here. Okay, and then you're like, oh my gosh, I'm in moles of oxygen. I'm so close to liters. And The only reason you're allowed to do that is because it's a gas. 1 mole of oxygen gas is 22.4 liters of gas at STP. So, what is that when you get there? Tell me what you put in your calculator. Okay, I'm reading your mind. 14.0 divided by 191.21 times 3 times 22.4. Oops, I just put 22.4. What did you get? 4.92 liters of oxygen. Okay, what was that we just calculated on paper in La La Land? Theoretically, it's like if we were perfect. Now we're really close to perfect, guys. But 9.42 is our liters of oxygen we should make from all that magnesium chlorate. But how much did we make?
3 liters.
I'm usually 3 liters. So how do I get percent yield? I hear you. 3 liters of oxygen over 4.92 liters of oxygen times 100. I like this.
60.976.
So what kind of lab rat are you? A
A
bad lab rat. Not bad, maybe just an off day, but you know, we'd probably say, sir, could you please do this experiment again? Or ma'am, can you please supervise him because he's not doing a good job? So, because I changed it. I just figured I knew this, I could do this.
better.
I do too. It makes my handwriting look much better. So, don't you wish you could just like change the setting on your pen? Okay, so this is our percent yield. Patch else on the back. 1 down. All right, ready for the next one? Yes? All right. Thanks, guys. So, I need a volunteer. All right, Courtney, come on up. Come on up. So, we're gonna require a deli area. Your area specifically. You just have a little fun today. So, I gotta fix these here. Help me separate that. Okay. Just intermission real fast. You know, talk to your partner about what you talked about. I didn't reset these before. My bad. Okay, intermission over. Intermission over. Look at my lovely diet bread. Diet bread. Little thin, the sandwiches. Yeah, sandwiches. My slices of peanut butter. Smell them?
You have a slice.
Slices, yes. Slices of peanut butter.
Are they
And then my slices of jelly. Okay, so how do you make the perfect peanut butter and jelly sandwich? Max.
Bread, peanut butter, jelly, bread.
Okay, 2 pieces of bread. I'm taking yours. 2 pieces of bread, one slice of peanut butter, and 1 slice of jelly, and then another slice of bread. Okay. You got the recipe. Yeah. She got the recipe. All right, where are the cheerleaders? I want you to make these sandwiches as fast as you can. Go. Okay. So bread, jelly. 1. Courtney. Courtney. There's a lot of people that have 3. There's starting people now. 4. We have 4. Wait, shoot. What's the other side?
What did you do?
What? So what stopped me from making my sandwiches?
You didn't have some of them.
We
Not
don't
enough what?
Bread.
What's that called?
Restricting.
Money?
Not enough bread.
That was that teacher-based salad.
No, we're not doing actual yield. We're not doing theoretical yield. The bread ran out. Okay. Did we have extra peanut butter and jelly slices? Yeah. So these are the excess reagents, and this nonsense that ran out.
Limiting the
Okay. So do you understand the concept of what would be limiting? It runs out first. It stops the process, and what would be in excess? It's just hanging out. Like, it's just excess. So would you want an expensive chemical to be the limiting one or the excess one?
Yeah.
Well, okay, don't forget, when things come into contact with
No, you want
another,
it to be the limiting one because you don't want like a ton of extra.
yeah, you don't want to waste money. Plus, this stuff's contaminated now. It's useless. We have to put it in the drain. Right? So, this extra stuff, it's all like peanut butter jelly fat now, right? It's not, it's been stale, flies on it, and nobody wants that this stuff anymore. So, that's what we're talking about now. Limiting reagent and excess reagent. I did not bring peanut butter and jelly sandwiches for you. This piece of bread. No, it doesn't look okay. Okay. So, but hey, we can do some more geometry on Friday. If you keep bringing stuff in. More geometry. Right, we will do it on Friday if you guys bring stuff. Okay, this is the last of like big slide notes. We're gonna do a problem after this. Okay.
Can I make like a little list?
I will make. But right now, focus on the task at hand. There's a little bit of information here, and then we're gonna do a big, huge problem. That covers everything. Please do not whine. My job is to educate you. Your job is to learn. Just doing my job. I'm making a list of reactants for our lab Friday, so we don't have anything that's limiting. Got it? And I just discovered chocolate graham crackers. Look, I don't get out much, don't I?
Oh no, I didn't know they were a thing. S'mores are really good if you use dark chocolate. No.
Okay, so personal opinions. I'll put this list up here.
I'd like to have a lot of chocolate. Is there anyone here allergic to the person?
So that will put this.
You can go sit in the hallway.
What if we already talked to our group? That also makes sense. Sorry. Okay, so you realize I'm not going to say a limiting reagent anymore. It takes too many syllables to say that. I'm going to say LR. Excess, I know it's 2 syllables, but XS is 2 letters. Excess. Got it? So when I put XS, it means excess. Huh? But I think you're saying XS, so it doesn't matter. Okay, so this is kind of your process. Like I told you how to do NIEs, there's a process. This is the process. But the process, this is kind of like simplistic rules, and we're going to go through how to do them momentarily. Okie dokie. Looking at my example, yes ma'am?
Is the ratio, is that the mole ratio? Or
Yes.
is it the mole ratio?
The mole ratio. From my example, if you can see my example, based off the pictures, who's the LR? The meat. The meat. You just assumed it was a hamburger. I heard patty. Is it veggie? This example is for vegetarians. So there were excess bread, cheese, and 1 tomato. Somebody didn't count. But why could there only be 3 products made?
Because only 3 times.
Okay, so that limiting reagent is controlling the number of products, the amount of product made. This other stuff is just an excess. So we're going to do a problem like this, but we're using chemistry. Yeah? Ready to move on?
Yes.
Okay, I will flash back here if I need to. This is the problem, okay? Doesn't look bad, but you're going to need a whole sheet of paper. Give yourself some space for this. So, very, very, very first thing for most of our problems so far has been to write what? The givens and the BC, okay? So before we even move on, I want you to write the BC or tell me what to write. And I'm going to write pretty writing for you.
Is it a single replacement?
Yes, how do you know it's a single placement?
Because I just see iron.
Because you just see iron, I heard iron, and copper 2 nitrate, yeah. So you know it's single replacement because there's not much else you can do with that. So let me tell you, up front, before I forget it, the common charges of copper is copper 2. So if I just say copper and you're like, she didn't tell me the charge, assume copper 2. Iron, assume iron 3. Nickel, 2. Those are the three that are really, really common. 90% of the time, that's what we get the charges. So you can see I did not tell you iron's charge, so what do you assume when you do the crisscrossing next?
It's 3.
Okay, so what is it? What's the whole shebang? FeNO3, 3, and copper. But copper by itself does not need a charge. Copper by itself is just solid copper. Okay, balance.
Need a 3 from the EFE.
Oh, hon, give me the nitrates first.
You need
You need a 2 in front of here and a 1 in front of here.
copper.
Okay, so we've handled the nitrates, and then tell me what I'm
You
putting.
need a 3 in front of copper.
And
2
2 over here. Okay. Okay, so step 1 done. BC done. Givens now. So this one's interesting because you've been given 1 given or 2 givens. This one has 3 givens. So the way you know it's a limiting reagent problem is not because it says what's limiting reagent. It's because it's going to give you information about one reactant and also another reactant. So you know normally it's like just information about one reactant. You just go for it. You're like, give me the moles of that reactant and then move on. This one you don't know who to move on with because you don't know who's the limiting reagent. So the very, very first step is to first take both of these pieces of information and convert them both to moles. And then we're going to do what? What's on your paper? You should write this down.
Then you're gonna do
Okay, so we're going to use the BC and some ratios. We're going to figure some stuff out. Okay, so anytime I say write something, this is like when I say write have and need, it's really helpful to do that because you're going to have a lot of stuff on here. So start me off. What do I do with this? Oops. What do I do with this to get me to moles? Tell me what that is. Where are you looking? So 0.85 grams of iron. Okay. So how many moles is that? You all should be calculating. If somebody's saying it, somebody else be calculating. Point 0.0644. I'm gonna go 5.8 just to hold it out a little bit so that I don't have any rounding error. Moles of iron. Square that little guy off, and this is literally how much you have of that reactant. It says that you have that many grams. That's how many moles you have of it. So write have up there. Because I'm gonna refer to this as the half need method, so this is why. All right. So what's the second reactant, and how do I get their moles?
5 milliliters of 0.51.
How do I get to moles from those two pieces? Molarity thing times.
Multiply the milliliters by liters.
Okay, so you want to get to liters first, so you can do that in your head. How many liters is that? Well, it's a lot less, right? So 0.005. So you're moving the decimal back 3 places. So that many liters times.
It's the
I just. Oh. So times by 0.51 what? Moles of copper 2 nitrate over 1 liter solution, right? So this big M again means moles per liter solution. So the liters and liters cancel. So now I've got moles of copper 2 nitrate. What is that? What's your mole count? Point 255 moles of copper nitrate. Sorry. Guess what, guys? This is how much you have of that reactant. All right. So when you're just looking at it right now, you're like, well, how do I know which one is going to run out first? Basically, the way we compare is we say, all right, let's look back at the ratio. Wrong markers. Looking back at the ratio. If I have 2 moles of iron, how much copper 2 nitrate do I need to fully react it all. Say again. So if I have 2 moles of this guy, so look up here, I'm pointing with my hand. 2 moles of that, I require 3 full moles of that, the copper to nitrate to react, 100%. So if I only had 1 mole of that, how much of that would I need? 1.5, so a half of that. If I had 0.5 moles of that, something less. Right now it's getting more difficult to do this math in your head. So instead of making you do that in your head, I'm going to make you write it. So what am I basically doing is I'm comparing the mole ratios. So how does that look when you write it on paper? It looks like, pretty pen, looks like us going from moles of iron to moles of copper to nitrate. So what's the ratio? What do I put on top? 3 moles of copper to nitrate on top over 2 moles of iron on bottom. So I'm comparing this number to how much copper to nitrate I need to fully react with all of that mess. Okay? So if that's 3 over 2, that means I'm going to multiply by 3 divided by 2. So I require, or I need whatever this number is of copper to nitrate to fully react with all of that. So tell me what that is. 0.0966. Stop in there. Moles of copper to nitrate. I'm going to scroll the board up for you here. So we just figured out that if we have that amount of iron, we need all that copper to nitrate to fully react with that amount of iron. So that's how much I need. Compare that need to how much you have of copper to nitrate. You need a ton. You only got 0.00255, right? So what automatically conclusion have you come to? It's going to run out. You need that much. You don't even have close to that. So who's your LR? That one, copper to nitrate. I know we're going to forget who our LR is, so we're going to write it up here. This one's our LR, this one's our excess. Right on top of your BC.
Why didn't we do anything?
For the second one, we are getting ready to. I'm going to prove it to you that it works.
So like, how did you already know that the iron is the
Because once I get one need, I compare it to one of the halves, the same half, and I can come to a conclusion from there. But I'll prove it to you writing a second time too. So I'm going to scooch my math down here. So what am I multiplying by here for this one? 2 moles of Fe on top, because this is talking about copper to nitrate, so I'm going to compare it to iron. So 2 moles of iron go on top, and then what goes on bottom? 3 moles of copper to nitrate. And tell me how much I need of iron. .06458. Got you. Moles of iron. Okay? So that's how much you need of iron. So if you need that much iron, oh no. You just told me that number again. Did you calculate this? Calculate this. I was like, hold on, that's exactly how much we have. Somebody calculate that. How much? 0.0017 moles. Jeez. Okay. So now I need. I was like, wow, that worked out perfectly. Okay, so this is how much I need of iron. How much do I have of iron? A lot more. So, aka excess. Yeah, making sense. So that's why the comparison's coming to play. And if you don't write the identity, you're like, have of what? You know, you don't know which one it is. So you have to write that, and then you cross compare. Okay, so we know that all this just to answer your first question. Who's limiting reagent, guys? The copper to nitrate. And we did that by the have-need method. That's what this method is called. Okay, so now after that, your job is to start part B like normal. But now that you know what your LR is, the key is to start with the LR moles. That's why we figured that out. Start with the LR moles. So what's my LR moles that I have? Say again? Who's my LR? Who's my LR? Copper to nitrate. And how much do I have of it? Okay, so this is my number I start with. That right there. So I'm starting it here, 0.00255 moles of copper to nitrate. So I'm just writing it here for us to know we start with it. And then let's go look at the question. I have to keep scrolling up and down, sorry. The question is, how much copper will precipitate from, nope, I skipped a nope, it's right there. How much copper will precipitate from the reaction? So what's our question? What's our unit we're looking for? So question mark grams of Cu from the reaction. So what do I have to consider? The VCE mole ratios. Okay. So mole ratios are what again? This thing keeps disappearing. I'm sorry, guys. What's my mole ratio between what I have and what I need, or what I'm going to? So I'm assuming 3 goes on. Oh, it is 3, yeah. 3 moles of copper on top, 3 moles of copper 2 nitrate on bottom, and I got that from where again? BCE. Don't forget, we did not just make that up. Mine just BCE is way up on top of the board. Okay, my question says go to grams. What's my next step? Yeah, and that might be. You're looking at me. You should be looking at the 63.55 grams of copper. And tell me how many grams of copper that is. You got to look at your periodic table to remember where stuff is, right? Alex. What is it? .162 grams of copper. I'm guessing that's what you said. Cool. All right, so that's answer B. We went from moles of our LR, moles of designated answer, to grams of that answer. Got our grams. Part C. How much of the excess reactant is left over? How do you think we're going to figure that out? Subtract. Subtract what?
What we have, what we know, the need from.
Subtract the need from the half. So half of the excess, subtract the actual need of the excess, and that's going to tell you how much is left over. So you guys figured that out by yourself. So proud of you. Left over. Okay, so how much did I have of my excess? Who's my excess, by the way?
The iron.
The iron. So I'm just going to put iron down here so you remember. All right, how much did I have of iron? You have this on your paper. 6.458 moles. Subtract. Not Lucas's answer. What was the need? How much did I need? Thank you. 0.017 moles. Okay, so what does that equal? What? 0.0 what? All right, that's how many moles of iron we have left over. But the question said how much excess was there? Go to grams. So much just means go one more step to mass. That's it. So what's that molar mass of iron? 55.85 grams of iron. Good. So this is me multiplying by molar mass. I just ran out of space. So that is Olivia. Sorry, depending on you now. Or Lucas. Lucas, do you think? 3 sorry, I didn't hear that. 3.505 grams. I'm stopping there. It's cool. It's close. 51 G. That's a gram, by the way. Okay. Okay, so breathe and then review with me what happened. What just happened? A lot. But tell me your process once again. We start at the top. BC is first. So we wrote our givens down. So we did BCE. And then you took your givens down. And then you're like, oh my gosh, she gave me 2 reactants. Then what do you do? Hold on, figure out the what first though? Have in what unit? Moles, right. So the moles of both. And then compare how? Right, ratios. So ratio comparison, blah, 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 blah. Okay? And then you compared your blank to your blank. Have to your need. Okay, so I'm just going to say compared have to need, and you had your aha moment where one was in excess. So you determine the LR in the excess, right? And then once you did all that nonsense, you're like, oh, I can start the problem, which is what's the number of grams of precipitate made? So what did you start with though?
Your
Half of the LR, right? You started with half of the LR. And then from there it's just stoichiometry. This is a more realistic example of stoichiometry because there's something involved that's more expensive and we don't just waste stuff. We put it in a ratio that's going to make it worth it, economically sane. Okay, this way, some people like. I'm going to put this information in an organized box. It's called a before, during, and after table. You guys have the information. You're telling me what to put in here. This is a way that I asked if people wanted to learn it, and some people wanted to. And I will use this method all the time. It's a more advanced method, but some people are organized in a different way. Tell me the reaction again.
2 FE 3 yields 2 3 plus 3C.
Okay, so I want you to watch this and decide if you like this or not. Is that good? Yeah? Okay, some of you guys are going to love this. This is how we do it in AP Chem. And I asked them, I told them, they said show it to you guys both ways and let you make a decision. They were in your shoes once, so they said this way makes sense to them. Before the reaction, so it's called a BDA table because it's before, during, and after the reaction. Before, how much do we have of both?
2 iron, 3
No. The numbers, you guys give me numbers, right? What was the number? 3.6, no, give me half in moles.
We have 0.064458.
06, say again,
4458 moles of iron.
thank you. And then copper to nitrate?
0.00255.
Okay, moles. Okay, so that's the half of both, right? How many products do we have before the reaction? We don't. We have nothing. The reaction's not even happened yet. Okay? So the way we do LRs in our head is we compare them to their ratios, which is their coefficients. If you have this ratio 2 to 3 existing, that means I need enough of this one to fully react with that one. Well, the cheat way to do it is that you take this number, you divide it by its coefficient. Can you do that in your head? It's small, right? Think small. This number divided by 2. Small. But is it that small?
No.
No, this one's smaller, right? The smaller number of moles after you've accounted for the ratio in which they exist is the LR. See, I didn't write a darn thing down. Right? I just mentally said, estimated, that number divided by that number divided by that, this one's smaller. This one's my LR, this one's my excess. Okay? It's nice if you know how to do it. If you mess it up, that's on you. Choose the other way. So during the reaction, what totally gets wiped out? The LR. So you know that during the reaction and after the reaction, how much of this is going to be left? 0. So how much am I subtracting here? All of it, right? 100% of it goes away. So it's reacting, every bit of that goes away. So I'm subtracting it from itself, 0.025 moles. But this reacts with this in what ratio? 2 to 3, right? The mole ratio of 2 to 3. So this reacts with that. So subtracting 0.00, what does it say? I missed a 5 there. 255. This reacts with that in a 2 to 3 ratio. Like you just told me. 2 to 3. So the LR number goes here because it's controlling everybody's destiny. It's controlling how much is subtracted here. It's also controlling how much is made there. So the LR number goes here in the ratio of this one to the LR. So tell me how much is left here. You don't have to calculate it. You have it on your paper. How much of excess is left over? Point. No, that was, no.
0.1.
Tell me in moles.
Oh, is it,
I can scroll back up. It's cool. This, we did that number, subtracting that number. Is that how much you guys got?
yeah.
Right? 0.06288. Okay. So 0.06288 moles excess. So literally, what did I just do here? I did half of excess, and did what?
Subtracted
The
LR.
need. The need, though, right? Isn't this right here how much I needed? That times 2 over 3. That's how much I needed. So this need is what I'm subtracting. you have all the information. We're just putting it in a table form. But this is quicker in some people's minds. So we subtracted half minus B and got the excess. Now, how much product? The only product it asked for was copper, so I'm just going to stick with that one. I'm making copper. I'm adding product. I'm producing it. But who controls how much product is made? So what number do I put here?
The 002.
Right, the 00255 number, but in what ratio is it made? 3 goes on top, so I'm in this column, to 3, right? So that's a 3 to 3 ratio. So how much is produced here in moles? I think we went to grams in ours, actually. Oh, it's the same number, my bad. 00255 moles. So if I wanted you to go to grams with that, we used our molar mass, and we got like, what did we get for grams of copper made? What did we get for grams of copper made? 162 grams, okay. So where is this step in our process? We literally took the LR, right here. We took the LRs, we multiplied by the ratio, and we got the moles, and we converted to grams. So we did that. But this is just a lot more writing. This is a bit more condensed. So your choice: choose the halving method that was presented first, or if you understand the BDA table is here as well. Yeah.
So why do you subtract by the LR for both of them?
Because the LR controls the world. It controls everything.
It does.
So the LR controls how much is used up of the other reactant, and it's controlled on how much is controlling how much is being produced.
Okay, so you subtract it by itself.
Because it needs to be going to 0 at the end.
Oh, yeah. Okay.
So if this conceptually makes sense, go for it. If you don't like that, stick with your other one. I just want to give you 2 options. Okay, we have about almost 15 minutes left in class. You guys have problems at 12?
Yes.
If you don't have it, I'll pull it up here. You have about 15 minutes to do some problems. I want to make sure that you have a good grasp of it. I would start at 1 or 2 here. 1 is just all ratios, do that on your own time. Starting number 2, if you guys have other questions, I'll come around for that. But if you've not started problems at 12, it's a little bit of a beast. It seems to get started. You should have started on it last night. Wednesday. I'll have to look again for you. It might be in the next tutorial. Yeah. If you are focused, then yes.
Sign up sheet to bring stuff in.
Oh, I need to put your name. I'll call your name.
Yeah, it's a bottom body work.
Yeah, I just want to get a sticker. I really don't. You can smell it again. So guys, if you want to talk to your group members and bring in stuff just for your group, like your lab group, that's fine. You just want to bring stuff in and donate it to the worthy cause of honors chemistry, that's fine. Just bring in stuff if you want to. Okay.
I'm crawling back. It's nice to have a break. Yeah, I'm just going to pull up. I'm just going to get chocolate from
I got. Go out like this. Oh, go
Right, we get it by Friday.
Jack. Oh, let me stop the video. Somebody just left. Wait, come back.